Okie dokie. Week 5, part 1, we begin to talk about Newton's laws. So Isaac Newton historically was basically a complete beast and ahead of his time and made lots of significant discoveries and that kind of thing. So we will hear about him and the physics and math that he developed frequently. So to talk about this, let's consider an object flying through outer space. An object flying through outer space would look something like, where's the black marker? So here's a planet, and here is some object, such as an astronaut, and they are lost here's their spaceship. their tether is broken, and they are simply moving in some direction, and they're very far away from the planet. They're going to keep moving in that direction and in that direction and in that direction and in that direction in a straight line forever. And that's weird, but we have seen sci-fi movies, and maybe that is reminiscent, or we've seen something like that, and so we can picture it at least. An object flying through air in the classroom, so this is what you have experience with, is being on Earth, not in outer space, and I'm trying to find it. Here we go. Not in outer space, and so here you are in the classroom, and you are, you finish your soda or whatever, and you're shooting a basket, and so you're used to seeing things travel in these curved paths. And so before people understood gravity and the laws of physics that we understand now, people kind of saw things moving in curved paths towards the ground, and they assumed, hey, everything moves in a curved path towards the ground, because in their experience on Earth, due to air resistance and gravity, they saw things slowing down, and they saw things moving in a curved path. So what can we say? Object flying through outer space, we could say straight line forever. And that's assuming that it doesn't come near any gravity fields. For an object flying through classroom, we can say that it moves in a curved path. And we can also say that it slows down, because if we slide something across the ground, we're used to it slowing down, and that's due to friction, either friction on another surface or friction through the air. But the difference between these two situations is, for objects in the classroom, objects that we see in our everyday life, there is some outside force. There's an outside force, and that's either going to be gravity or friction. Those are the things that we actually do experience: gravity plus friction. Whereas in outer space, deep outer space, it would be away from a gravity field, and it would be in outer space, an empty vacuum, and so an object would not experience friction, and it would travel in a straight line forever. And so Newton, way back when, said, you know what? Objects, so here's the full law. Objects in motion, sorry about my writing here, tend to stay in uniform straight line motion. Uniform meaning constant speed, straight line motion, unless acted upon by an outside force. There's no comma there. I definitely need more space. Unless acted upon by an outside force. So he came up with that way back when, and think about this and how it applies to these two situations. So with no experience of seeing this or hearing about this or whatever, he sort of intuited that that would be the case in this situation. And we see things slowing down and moving in curved paths, only because gravity exists on Earth and friction as well. Okay, so before we move on to mass and inertia, what is a force? Because you've used that word in English language, and when I say it, you probably have some understanding of what it means. And I love this definition for force because it's so simple, and it's simply a push or a pull. And we can use that as our technical definition for force because it's basically, well, I'm going to stop trying to explain it. It's a push or a pull. But when we talk about the difference between mass and inertia, so sorry, this is getting a little messy. But when we talk about mass, mass is the amount of matter. We can also, if we want to get super non-technical, the amount of stuff. If you want to think small, it's basically the it would come down to the number, the amount of mass that something has would come down to the number of protons, neutrons, and electrons in an object, if you were to just add them all up, and it would be a very large number. Inertia, so anything that has mass will have inertia, and we say that mass has two properties. One is, I'm going to run out of space, I'll just say it. For mass, we say one property that mass has is that it resists acceleration, and we call that inertial mass. And the other property of mass is that it attracts other mass, and we call that gravitational mass. So when we talk about inertia, we mean the tendency to resist acceleration. Tendency to resist acceleration. The more massive something is, the more it's going to resist acceleration. And so you can imagine yourself, you're driving along the road, and there's this big semi truck, and the battery went out or something, and the driver's like, "Hey, will you push me?" All right, I'm going to try to pop start my semi truck. Even though the wheels aren't locked up, it would be very massive, and so it would be very difficult to move. So before we talk about mass and weight, let's talk about this. So I do this demonstration in class, and if you're just watching the video, it won't be as exciting, but there will be two boxes, and one is going to have a bunch of stuff in it, and it's a bunch of masses, right? And then one's going to be empty. So empty, and then this one's full, and they're sitting on a table, and my challenge to you, the student, is which is empty, which is full. You cannot lift the boxes, and you cannot open the boxes. And based on that, you have to determine which is full and which is empty. And the students, that's you, tend to think this is really easy. And what they do is they just kind of slide the box back and forth. And when they slide the box back and forth with this one, it's easy to do, and when they slide the box back and forth, it's difficult. And so we can say large force for this, and we can say small force for this, and they just intuitively, without without Newton's second law, without the definition of inertia, you, just having lived on this planet for as many years as you have, understand that if you have to use a larger force to move this back and forth, it's full. And I picture students under the Christmas tree messing around with their presents, trying to figure out what's inside. So anyway, you have an intuitive understanding that something with more mass is going to resist acceleration more, meaning more mass, more inertia. And so you can do that without actually lifting it up and testing the weight of the object. So let's talk about mass and weight. Units for mass, we use kilograms. Okay, grams are related to kilograms, of course, but in science we definitely use kilograms. And weight, so we're used to, being America and all, we're used to pounds, and we're going to try not to use pounds. In physics, weight is actually a force, and so we use the units of newtons. I know Newton was so cool that he got his own unit named after him. And it's a measure of force, and we'll learn much more about that. So when we say does it change, meaning the mass of an object is never going to change because it's still the same object. So the answer is no. But if we talk about weight, then yes, the weight of an object does actually change because weight is just the force due to gravity. So we don't really have a place for the definition of that. I think we've already done this. But let's just say force due to gravity. And so the force due to gravity changes. The farther you get away from the surface of Earth, the less your weight will be. It's like the Jenny Craig program, you know, go to the top of Mount Everest, and you're, besides the fact that you'll exert yourself in getting there, the force due to gravity will actually be less. Okay, so what is it? When we're talking about mass, well, it's the amount of matter. So it's some quantity of stuff, whereas weight is a force. So the force acting on that stuff. And then do astronauts floating in deep space have it? And they would definitely have mass, but if there's no gravitational field, they will not have weight. So this and this are related to one another. Okay, so let's talk about weightlessness, because an astronaut being in deep space, that actually hasn't happened. All of our astronauts have been in orbit, you know, or gone out to the moon or whatever, but deep space is really far away. We're talking like way away from our solar system and our sun. So what is weightlessness? Well, we will talk about this much more later, but the idea is that here's an astronaut, and let's put this astronaut, they're in a spacesuit, but let's put them in a spaceship as well. So here is the spaceship. It's pretty tight quarters in there, but that's okay. They have a little window they can see out. And the spaceship, actually wait, there's no jets or boosters or whatever. It's just quote unquote floating. So what's going on with weightlessness is there is a force due to gravity that would be in this direction. And these are pretty far away, so they're outside of the atmosphere. They're in orbit. Gravitational force is not nearly as strong as it is here, but there's still some pull. And so the spaceship is actually falling towards Earth, and the astronaut is falling towards Earth, and the astronaut's spacesuit is falling towards Earth, but they're falling at the same rate. And so the astronaut is just kind of floating within the spaceship because they're both falling at the same rate. And I know that's weird to think of, but imagine an elevator. And so here's Joey in the elevator, and some physics student is so sick of hearing about Joey that they take some scissors and they cut the cable. So here are scissors, and they cut the cable. And Joey is falling, and the elevator is falling, and Joey, as he's falling, would just kind of be floating within the elevator. So there's Joey again, and they're both, he's frowning because he's falling to his death. They're both floating, and so, I mean, they're both falling, and so it would seem as if Joey is floating within the elevator. And the same thing happens with an astronaut in a spaceship. We will talk more about orbits later. There's more to it. I think I'm about out of time, so let's take a look at page 2. I have definitely been rambling. Alright, so for page 2, I think we're going to have to do this in a separate video, so stay tuned.